Okay, so in this chapter we'll study forces. Newton gave us the laws of motion. He gave us three laws that govern motion. Okay, he did many other things too. Newton was a smart man. He gave us the laws of motion. He also discovered the law of gravity. He invented calculus, and he gave us he made great contributions to the theory of light and color. All right, so let's look at the Newton's laws of motion. The first law states that, so what this is showing you is a air hockey table, and if you played air hockey, you can get the puck moving and it will feel like it's not slowing down. So what Newton's first law states is when no net force acts on an object, its velocity is constant. That is, if there is no force acting on the object, it will maintain its velocity. Okay. So, for instance, the weight is being balanced by the upward force that the air is exerting, and because this puck is riding on a layer of air, there's no friction. So this approximates this to a good approximation is no net force acting on the object. Anyway, so the first law says if force acting on an object is zero, velocity is constant. Okay, that's the first law. The second law states what happens when the force is not constant, not zero. So when you have a force acting on an object, then the object accelerates. Okay, and you see the larger the force, the greater the acceleration. The larger the force, if the mass is greater, the acceleration is smaller. Okay, so larger the force, larger the acceleration for a given object. Now this is a vector equation. Okay, so the acceleration is in the same direction as the force. Okay. Now in SI units, mass is measured in kilograms, acceleration in meters per second square. So force is kilograms times meters per second square. And this combination of units is called a Newton in honor of Mr. Newton. All right, so the first law says if force is zero, velocity is constant. That means acceleration is zero. And the second law tells you when the force is not zero, you have an acceleration. Okay, so the SI units is what we'll mostly use, which is Newton. In the US units, the units of force are pounds. The units of mass are slugs, and acceleration is feet per second square. Newton's third law says the following: if an object exerts a force on another object, this other object exerts an equal and opposite force on the object. So you might have heard it like so, stated so: action and reaction are equal and opposite. Here's the action, here's the reaction. So when you take off on the swim, you push on the wall and the wall pushes you back. Similarly, when you're walking, when you're walking, you're pushing back on the ground and the ground pushes you forward. Okay, so we use that this Newton's third law all the time. So again, action and reaction are equal and opposite, and action and reaction act on two different bodies. Okay, so that's Newton's third law. Now here we'll see the superposition principle. So the question is, what happens if on an object multiple forces are acting? So on this object there is this force acting and this force acting. And what the superposition principle says is the net effect on this object is the sum of these two forces. So you add the two forces, there's the net force. All right, so the motion of this object would be the same whether this single force acts on it or these two forces act on it. And that's the superposition principle. Okay, so you can't tell on that object if that single force acts or these two forces act. Okay, so the net effect will be the same. Okay, so whether on the object these two forces act or this single force acts, the effect will be the same. Okay, and that's the superposition principle. So again, if multiple forces are acting, just add the forces up into a single vector, and that's the net force on the object. That's the superposition principle. All right, so here's a simple problem on Newton's second law. Again, force is mass times acceleration. Okay, so in this problem, a 440 gram can of food is given a shove on the frictionless surface and is observed to accelerate at 1.5 meters per second squared. Okay, so they've given you the mass of the object and they've given you the acceleration, and you just calculate the force, take the product of the two. Now the mass has to be converted to kilograms, so 440 grams is 0.44 kg, that's 0.44 kg. And the acceleration is 1.5 meters per second squared. And this works out to, so this works out to 0.66 newtons. Okay. So, and that's the problem. And again, make sure you study these problems carefully. There'll be similar problems on the exam. Okay, Newton also gave us the law of gravity. What he said was, every object attracts every other object in the universe. Okay, so let's say this guy attracts him, and this guy, by Newton's third law, will attract him. So if this guy attracts him with a force of 10 pounds, this guy will attract him with a force of 10 pounds. So for instance, let's say if your weight is 150 pounds, what that means is the earth attracts you with a force of 150 pounds. Okay, and according to the third law, you attract the earth with a force of 150 pounds. Okay, okay, so this is, and what Newton gave us was a formula to calculate the magnitude of the force. So the magnitude of this attractive force, so this attractive force, the red arrow, the magnitude of that force is G, a universal constant, gravitational constant, times the product of their masses divided by the distance squared. All right, this is called a universal constant because it's the same constant whether it's two people attracting each other or two planets attracting each other. Okay, so that's why it's called the universal gravitational constant. And it turns out that it has a very small value, and that's why the gravitational force is very weak. Okay, so there's the value of the gravitational constant. Now there are four fundamental forces in nature: the strong force, the electromagnetic force, the weak force, and gravity. Strong force, electromagnetic force, the weak force, and gravity. And gravity is the weakest of those four forces. Okay, now we'll consider some forces. Okay, so like we said, every object attracts every other object. So the earth attracts, so the earth is attracting this watermelon, and the direction of the gravitational force on the watermelon is towards the center of the earth. The magnitude of this force, the strength of this force is called the weight, and that's just equal to the mass of the object times the acceleration due to gravity. That's what that is. So the weight of an object is just the magnitude of this gravitational force. So let's look at this laptop. The earth is pulling down on the laptop. The earth attracts the laptop, and the laptop is not falling down because this man is exerting equal and opposite force in that direction. Okay. And this force, which is perpendicular to the hand of the person, is called the normal force. Okay. So that's the normal force, and that's, you see that in many situations. So here's an object sitting on a table. The earth is pulling it down. Okay, and what's preventing it from falling through the table is the normal force. Okay, so it's often written just N or F for force and subscript N. So that's the normal force. And since this guy is at rest, this normal force is equal to that, the weight of the object. We will encounter the term tension quite often. Okay, so here is a string that is taut. A taut string is said to be under tension. So think of a stretched rubber band. Okay, this string is attached to this block, and it's attached to this block on the end. So what would the rubber band do if this was a rubber band? The rubber band is trying to shrink. So the rubber band is pulling this object in this direction, this object in that direction. So the tension in the string is applying a force on whatever it's attached to. And the direction of the force is such that the string is trying to shrink. Okay. So if there was a 10-pound tension, that means the string is pulling this object with a 10-pound force in this direction, and this object with a force of 10 pound in that direction. So you'll see muscles under tension, and we'll come to that. All right, on this object, this barge, this force, this tugboat applying a force, this tugboat applying a force in that direction, and there's a drag force from the water, the friction force from the water in that direction. So on this barge, there are 3 forces acting. 1, 2, and 3. The friction force. Okay. Now, as long as the barge doesn't spin, the barge can be represented by a point object. And that's what we're doing here. Okay, so the barge is represented by this point, and the 3 forces are shown here. There is F1, there is F2, and there's the drag force, okay, which is that one. So there are 3 forces acting on it, and you just add up the 3 forces, and that is the net force acting on the object. So this is the net force acting on the object, and the barge accelerates in that direction. Okay, this is called a free body diagram. You just show the essential forces, and where they're acting. And if the object is not spinning, that means all the forces are acting through the center of mass, and this can be represented as a point object. Now we'll talk about friction forces. So let's say here's a wooden crate sitting on the floor. If you try and attempt to push the box, let's say you apply a 15-pound force and the box didn't budge, that must mean that there's a friction force of 15 pounds in the opposite direction that prevented it from budging. And when this thing doesn't move, this friction force is called a static friction force, and it's written with a little f, and the subscript s is telling you it's a static friction force. Now here's the deal with the static friction force. Now initially you applied 15 pounds and it did not move, so that was 15 pounds. You apply a 25-pound force and it did not move, and so this friction force increased to 25 pounds. So the static friction force can change from anywhere from 0 to a maximum value. Okay, and the maximum value will be such that when you apply the maximum force, this box will just break loose and start moving. All right, so the static friction force can be anywhere from 0 to a maximum value. Now, the friction force arises because of the rough surfaces, and these atoms form loose bonds. Okay, and so to get it moving, you have to sort of break all those bonds. And you can see that the friction force will depend on what two types of surfaces are in contact. So between the wooden crate and the concrete floor, the friction force would be much greater than for, let's say, a block of ice sitting on an icy surface. Okay. So the friction force depends on the surfaces that are in contact. Okay. And and also, if, for instance, if you push down on if somebody sits on the block, then the friction force will be greater. Okay. So it'll depend on the surfaces in contact and how hard they're being pushed against each other. And it turns out that it's independent of the area in contact. Now, once you get the box moving, then the friction force is called a kinetic friction force. Okay, so once the box is moving, the friction force is called kinetic friction force, and the kinetic friction force is always smaller than the maximum static friction force. Okay, so it's always, so once you get the box moving, it's easier to keep it moving. Okay. All right, so this tells you the static friction force is less than this maximum value, and this maximum value is the coefficient of static friction times the normal force. So that's the maximum static friction force. The maximum static friction force is mu s times Fn. The kinetic friction force similarly is given by coefficient of kinetic friction times the normal force. Okay, again, so here is the push you applied, there's the friction force, static friction force in this case, so the object is not moving. And in this case, the object is moving, and there is the kinetic friction force. Okay. So what this graph is showing you is, so see, this is the static friction force going from 0 to its maximum value. Okay. And once you apply the maximum force above the maximum friction force, it breaks loose, and this is the kinetic friction force, which is smaller than the maximum static friction force. So these guys, the mu s and mu k, are the coefficient of frictions. Okay. So here is mu k and mu s, and these are given for various surfaces in contact. So for rubber on dry concrete is 0.7, and rubber on on dry concrete, the static friction force is 1. Okay. Now, so this is related to the fact that okay, this stuff is important for braking purposes with your cars. Okay. If you don't lock your car, this is the friction force that's coming into play, and it'll stop your car faster. If you lock your cars, this is the friction force that's coming into play, and your car takes longer to stop. Okay. What these numbers mean is the following. So if you have so let's say you have 100-pound blocks sitting on the floor. So the normal force would be 100 pounds in this case. Okay. So if this is a rubber block sitting on dry concrete, a 100-pound rubber block sitting on dry concrete, the force you need to apply to keep moving it at a steady velocity should equal the friction force. And the friction force would be mu k times the normal force, which is 0.7 times 100 pounds, 70 pounds. So what this number means is, if you have 100-pound rubber blocks sitting on dry concrete, to keep it moving at constant velocity, you have to apply a 70-pound force. To get it started to move, you have to apply 100-pound force. So if this was an ice block sitting on ice, a 100-pound ice block sitting on ice, all you need is 3 pounds to keep it moving. And you need 10 pounds to get it started. So that's what those numbers mean. Now, for instance, in biology, here's an application. So during a deep tissue massage, what the masseuse does is he or she will press down on the patient, so the normal force is large, it's the weight and stuff, and so there's a friction force, and the friction force is larger because of the normal force. So to give a deep tissue massage, you're pressing down, the normal force is large. During a massage, the normal force increases if the massage therapist supports more of her weight with her hands. This causes more friction because Fn is larger. To compensate, a lubricating oil. Okay. So to compensate, a lubricating oil with a low coefficient of friction is used. Okay. Now we use muscles to exert forces. Okay. Now the thing about muscles is they can only contract. Okay. So you always have two sets of muscles. Okay. A muscle is called a flexor muscle if it brings bones closer together. So when this muscle contracts, it brings this bone closer to that bone. It brings it brings these two bones closer, okay, when this muscle contracts. And this muscle, the quadricep, is the tendon is attached to the tibia, and when this contracts, it stretches your leg. Okay, so, and that's called an extensor muscle. A flexor brings two bones close together, and extensor brings the bones apart. Okay, again, muscles can only contract, and when this contracts, it brings the leg further out, so it stretches the leg from here to there. And when this muscle contracts, it brings the muscle closer in that direction. Okay, you have hundreds of muscles in the human body, allowing forces to be exerted in almost any direction. So for instance, there are several muscles in the shoulders, and the diagram is not very clear, but all these muscles are applying, these various muscles are applying all those forces, and the sum of all those forces, that's the sum of all those forces which is in this direction. So all these muscles combine to give a force, apply a force in that direction, in the horizontal direction. By varying all those forces, you can apply a force in any direction. Okay, so the purpose of all those different muscles in your body is to apply forces in various directions, so the net force can be in any direction you desire. In addition, you have tendons, sometimes carry forces exerted by muscle to another point, and maybe they also change direction. Okay, anyway, all the muscles in your body are used to apply forces in various directions. We also have something called sphincter muscles. Sphincter muscles are sort of spherical muscles. They close in on themselves, and their purpose is to open and close pouches. So for instance, there is a sphincter muscle there that'll close the stomach and prevent acid from flowing back to your esophagus. Okay, so it prevents acid reflux. Okay, and so the sphincter muscle, so these muscles um, uh, open and close pouches, sphincter muscles. So now that we're familiar with forces, let's apply them to some biological application. So let's say this person has has a broken back and has broken vertebrae. Okay, you don't want the broken vertebrae damaging the spinal cord. So what you want to do is, while the vertebrae heal, you want to stretch the backbone. And so here's a striker frame, and the way it works is there are two screws attached to the temple area, and here's a weight hanging. Through a wire, you can have a weight hanging, which is stretching the spinal cord. So which is stretching the spinal column. So it prevents the vertebrae from damaging the spinal cord. Okay, so striker, it is necessary to stretch the spinal column along its length for the vertebrae to heal and to prevent broken vertebrae from damaging the spinal cord. The force applied is equal to the weight hanging on the right. Yeah. Here's another multi-function traction system. So here is a broken bone, here's a broken femur, and the muscle, remember, will contract and will bring this bone against each other, and they won't heal properly. Okay, so you want to prevent that from the muscle contracting and not letting the bones heal properly. So what this system does is, this part holds the lower leg, is supporting the weight of the lower leg, and the tension in this wire is pulling on this. So here are two screws attached to this bone, and it's pulling on that, so it's working against that contracting muscle, and so this bone can heal properly. Okay, so here's a traction system which will aid in healing. Okay, now sometimes forces can cause rotation. So let's look at the torque. So for instance, we've all used a wrench, and if you apply a force like this, it'll turn this unscrew this nut. Okay. Now, forces can cause linear motion and rotational motion. The effectiveness of a force in producing a rotation is called torque. Okay, so torque is the magnitude of the force times the lever arm. The lever arm is the perpendicular distance from the line of action of the force to the point about which you're calculating the torque. So in this case, that's the lever arm. That's the lever arm. For this case, that's the lever arm. Okay, so in this case, the torque would be small. So the torque is denoted by tau, and it is force times the lever arm. The lever arm, it's also called the moment arm. So the greater the lever arm, greater the torque, and greater the effectiveness of rotation. Smaller the lever arm, smaller the torque. Okay, so for a given force, you want to maximize lever arm. So for instance, in this case, this guy has, so you're calculating the torque about this point, there's the force, there's the lever arm. In this case, the lever arm is the same, but the force is smaller. So if you apply a force, the same force here, the lever arm is smaller, okay, and the torque is smaller. So it's better to open a door by pushing it there rather than there. All right, so now, so for an object to be at rest, that is conditions for equilibrium. So in this case, you see, if you apply two forces like this on this object will be at rest because this is canceling that. And in addition, the torques of these forces, if you calculate about any point, are zero. So for instance, if you apply the same two forces here, the two forces add up to 0, except that this force is going to rotate this object clockwise, and this guy is also going to rotate it clockwise. So in this case, the torques don't add up to 0. Okay, so if you want this object to be at rest, not only do the forces need to add up to 0, the net torques need to add up to 0. Okay, so we'll use this to calculate various forces. Okay, so for instance, here's you're holding a physics book, and let's calculate the force that your biceps exert. Okay, so here's a free body diagram. This bone of your arm is denoted by that. There's the weight of the bone itself, or the arm itself. There's the weight of the object you're lifting, and there's the force the bicep is exerting on the bone. And there's the pivot point. We're going to calculate the torques about this pivot point. Okay, clockwise, if a force makes an object rotate clockwise, that's taken as negative torque. And if an object makes if a force makes the object rotate counterclockwise, that's taken as positive torque. Okay, so the bicep is going to rotate it counterclockwise. This is clockwise torque. Okay, and torque is the force times the moment term. So you would have FB times 4 centimeters, and you would have to convert that to meters, minus weight of the arm times 15 centimeters, and weight of the book minus weight of the book times 40 centimeters. And if the arm is at rest, these torques should add up to 0. Okay, so if you know these two guys, then you can calculate the force that the bicep exerts. Okay, and it's worked out here. So there's the weight of the arm, which is 2.5 kg, 24.5 newtons. Weight is mass times gravity. And you put all those numbers together, the force that the bicep exerts, so the weight of the book is, the mass of the book is 4 kgs, the mass of the arm is 2.5 kg. You put all those numbers in, and the force that the bicep exerts is 484 newtons. See, the weight of the book is 40 newtons, and this is 480 newtons, 12 times greater. So to lift up 1 pound of book, you have to apply a force 12 pounds of force for every pound to lift. This force is 12 times greater. All right, so and this is a common theme in muscles. And the reason being, since muscles can't contract too much, they have to apply a much greater force. So in order for the clockwise torque to equal counterclockwise, its force must be much greater. The bicep is said to be at a mechanical disadvantage, as are most of the muscles in the body. So most of the muscles in the body are at a mechanical disadvantage in the sense that they have to apply a much greater force. So like you saw in this case, to lift a 1 pound book, you have to apply a 12-pound force. Yep. Now let's show this. Let's see another example about good posture and why you need good posture. So here's your upper body. Okay. There's the center of gravity of your upper body. Okay, and that's your pivot point. So if you have good posture, this thing models the weight of the upper body is right above the pivot point, and there's 0 torque, and this is the best position to be in. Okay, there's very little strain on your body. What if you slouch? Here's you slouching. Okay, there's the center of gravity of your upper body, and there's the moment arm. So you're upper body is trying to topple you over. It's providing a clockwise torque. And so to prevent you from toppling over, your back muscles have to apply a force. The back muscles are applying this force. Okay, and there is the moment arm for the back muscle. Okay, so the back muscle and moment arm for the back muscle. So that's a counterclockwise torque, so that's positive. And this is your weight of the upper torso times there's the moment arm. So moment arm for the upper torso, for the torso, and that should be equal to 0. So back muscle RB equal to RT. Okay, and so the back muscle, the force the back muscle applies is the weight of the upper torso, the moment arm of the torso, divided by RB. Okay, now this moment arm is small, this is small, and the more you slouch, the bigger this is, and the more strain you put on your back. Okay, so the more strain you put on the muscle. Okay, so slouching is not good. Here's another example. Okay, so again, if you lift with your back, this is what we mean by lifting with your back. So if you lift like that, again, there's the pivot point, there's the weight of your upper body, and there's the weight of the box you're carrying. So this force and this force are trying to topple you this way. So, and this back muscle with the very small moment arm is trying to hold you back. So when you lift it this way, there's a huge strain on your back. On the other hand, if you lift with your legs, so to speak, okay, what is, so again, when you lift with your leg, this weight, so the weight is close to the pivot point, and this is providing a clockwise torque, and the muscle, this muscle is contracting and providing the counterclockwise torque. Okay, and the muscle can bear a large force, and anyway, its moment arm is small. So this is the best way to lift an object. Lifting it with your back puts a huge strain on your back. The last topic we'll consider is uniform circular motion. So when you go in a circle, you're driving in a circle at constant speed, the direction of your velocity is changing. The magnitude is not changing, but the direction of the velocity is changing, and you have a centripetal acceleration. And the centripetal acceleration is speed squared divided by r. It's called centripetal acceleration because the acceleration points towards the center. Okay, and to have any acceleration, you have to apply a centripetal force. Mass times the acceleration. All right, so we'll use this idea in ultracentrifuges. So for instance, let's say if you have a glass of muddy water and you let the glass sit, the mud will all eventually settle down. Okay. Now, but it takes time for the mud to settle down. Now, to make this mud settle down faster, if you make gravity stronger, it would settle down faster. Okay, and that's the idea of a centrifuge. So what you do is, so you put your stuff in a test tube and spin it around real fast, and that effectively gives you a large gravity in that direction. Okay, effective gravity. And you can actually spin these centrifuges fast enough. So here's a centrifuge, an ultracentrifuge that spins around 150,000 revolutions per minute. And if you follow through this thing, it gives you an effective gravity of 1,000,000 times g. It's like making the force of gravity 1,000,000 times greater. And so it'll settle much, much faster. And that's the idea of centrifuges. All right, so that finishes this chapter. Okay, and again, study the slides carefully. All the answers to all questions are in the slides. Okay,